Last time we worked on section 2.1, we're going to finish that up this time, and we stopped sort of in the middle of doing Roman numerals. So just as a reminder from Roman numerals, these were the different values that we had. And the Romans had two basic properties in their system. One property had to do with subtraction, and so anytime that they had a number that we would call a 4 or a 9, they would use a subtraction feature to avoid writing any symbol 4 times. That's the basic idea. And also that means anytime you see a smaller symbol before a larger one, the subtractive feature is actually happening in the number. And then they also had this multiplication feature that you may or may not have actually seen before that allows us to write numbers that are larger than basically than 3,000. 3,000 we could have written as 3m's. Once we get to 4,000, there's not a way to do that. So when we're dealing with something like 9,000, we use the number 9, ix, and then we write 1 bar over it to represent 1,000. And if we wanted to do a million, we'd do 2 bars on top. Everybody kind of remember where we were talking about with the Romans? Okay. All right, so let's do this number. This number is MCMX. And same kinds of questions that we dealt with last time with the other numeration systems. First, what number is before this value? And then second, what number comes afterwards? So, what numeral comes before MCMX? What would you do? So I'm purposely avoiding part C, which is changing the number right now. How did we do it when we were looking at the other numerals? Do you remember the basic idea of what we were doing?
Subtracting one?
Yeah, like the idea of subtracting one. And we were looking at the very end, right, Rachel? So we looked at the very end. The last numeral here is the numeral for our number 10. So we need that 10 to be a 9. So what would we do to change that? Would we?
No.
We'd put an I in front of the X. All right, so the M and the C and the M, those don't change. It's only the numeral at the end, the X, that changes. And while we want to write it as a 9, we don't want to write 4 symbols, so we wouldn't write V and then 4 I's. We would write an I and then an X for the symbol 9.
So even though that's 4 symbols, that didn't bother them now?
It's not the 4 symbols, it's the 4 repeated symbols.
Okay.
Like a same symbol, the exact same symbol 4 times in a row.
Okay.
That's what they're not going to have. Yeah, good question. All right, how about part B, the number after? What do we get to do? What do we do to get the number after? Right, we'll just include an I at the very end. So we have MCMX, and then it's I. So these two numbers, A and B, actually look very much the same. And if you were dyslexic, that would be a problem, wouldn't it?
No.
It might not be so good. But yeah, we just end up having the I before the X or the I after the X to represent the numbers before and after. So finding a number before or after is actually pretty clean in their system. That's not a bad thing to be handling. Let's turn this into our numerals. So when we're looking at the Roman numerals, I mentioned very first thing today that when you have a smaller numeral before a larger one, that you've got a subtractive feature. So we have that in this problem going on, right? Where do you see a smaller number before a larger one in this number?
C before the second.
Right, the C before the second M, right here in the middle. Let me try that again. So what does the M at the beginning represent? What number is that?
1,000.
That's 1,000. The fact that I have a C before an M is a subtractive feature. The C is the number 100, and the M is the number 1,000. So if I subtract them, I get 900. Yes. So I've actually got 100 here, and then 1,000 here. And since the number 100 is before the number 1,000, I will subtract to get 900. And then my X at the end gives me 10. So what Hindu Arabic numeral is this? Yes, 1,910, which looks an awful lot like our dates. So this kind of a numeral you might actually see on a building. It would be reasonable to see something like that. All right, we're going to go the other direction. We're going to do the number 1,492,019. And we're going to write this in their numeration system. So starting with, I've got a number bigger than 1,000 here, right?
Yeah.
So I'm definitely going to have some bars, either a double bar or a single bar or maybe both going on in the problem. So let's talk about the number 1492 as a whole quantity. We talked about last time that if the number, like ignore the 019 at the end completely. If the number were only 1492, right, we wouldn't need any bars, correct? Because I have a way to get the number 1,000. How do I get the number 1,000? That's an M. So let's start with ignoring the 0, 1, 9 at the end. This would be an M. How do I get 400?
No, C, I, C. No, not I, C.
No.
L, no.
Okay, so let's use, without using C's and I's, just tell me what you're thinking with the numbers without the numerals. How do you get 400? You're going to use a subtractive feature, right? What number values are you subtracting? I don't mean C's and I's and M's and whatevers. 100 and 500, right? So the way that I get 400 is what I need is I need 100 listed first, and then I need a 500 listed after that. Agreed?
Yeah.
So what is the symbol for the number 100? C. And what is the symbol for the number 500? D. So C and then D gives me the number 400. Everybody good with that? Okay. Let's do the same kind of a thinking with the number 90. How do you get 90? Subtraction. 100 minus 10, right? So we put the 10 before that. How do we get the number 10? And what is the number 100?
C.
C. Excellent. How do I get the number 2?
2 I's.
2 I's. So this number right here is the number 1492, like Columbus and the ocean blue. 1492. All right? But I want it to be 1,492,000.
3 bars.
No? How many bars?
2 bars.
2? 1. I have 1.
Oh, because you already have it.
Because this is in the thousands place, right? It's this number times 1,000. As awkward as it feels to say it, and because we don't speak this way, this is 1,492,000. Right? Okay, ignore the 1 for a moment to think about it if it helps you to think about it. This would be 492,000. Agreed? So the way we get the number to be times 1,000 is we do 1 bar. So there's 1 bar on top. Now, if that number, instead of starting out as 1 million, started out as, say, 5 million, then I would have to do something different. Agreed? Because I don't have a symbol for 5 million. I have a symbol for 5. It's a V, and I can put 2 lines over it to get million. But I don't need that on this one because the number is simply a 1. All right, let's do 19 then. How do I get 19? All right, so keeping in mind that I've got a 1 here, so that gives me 10, so that's X. And then how do I get 9? IX, right. XIX at the end. Any questions on that? Okay, so I should have brought my blocks. I'll bring them next time. The next thing we're going to talk about is we're going to talk about base 10 blocks. You've seen them before. Base 10 blocks are a really good visual. Money is another really good visual, but base 10 blocks allow us to go sort of a bigger in dimensionality than money does, at least in terms of our dollar bills. So there are 4 different visuals when we're working with base 10 blocks. The first one is called a unit block. So it looks like a little square. And it has a value of 1, right? And we could also talk, well, I'll talk about that in a minute. In our base 10 number system, if we took 10 of these unit blocks together and we stuck them end to end and we had sort of attached them, that's what we would call a long. And when we draw a long, we don't have to draw the individual units out. We just draw it to look like one long piece. And in your mind, you have to remember then, since this is base 10, there's 10 of them that are stuck end to end. So the first one would be the equivalent of a penny, and the second one would be the equivalent of a dime if we were talking about money, right? All right, the next one is a flat. So a flat takes a long, and it makes it 2 dimensions instead of just 1 dimension of length. So I end up getting something that looks like a large square. And it has the value, oh, the long has the value 10. I'm sorry, I didn't write that down. A flat has the value 100. So if I were to draw it all in, sort of gridded in, I'd have 100 little blocks, 10 long and 10 deep, or 10 wide and 10 long, or something like that. And it would look more like a square than mine does, because that's not a very good square. A block has a 3rd dimension to it, so I get width as well on that one. And so I get something that looks like that same square that I just had before on the flat, but then I have to make it 3-dimensional. So it looks something like this. So it's 10 long, 10 wide, and 10 deep backwards now, which means it has a value of 1,000.
Are these those blue blocks?
Hmm?
Are these those blue blocks?
The ones that I have are red, so it just depends on what you're using. And what I have and I'll bring is I actually have base 10 blocks just like these. But I also have base 3 blocks, which we're going to talk about in a little bit. So this base block kind of an image works for any base system you want. We talked about using base 10 last time because we have the 10 fingers and so forth, and how if we had only 8 fingers or that we didn't have thumbs, we would use a base 8. You can do this with any of these systems. There's nothing special about base 10. It just means that instead of having one little unit stuck to itself 10 times, you'd have one little unit stuck to itself 8 times in base 8. If we were doing a flat in base 8, it'd be at 8 wide and 8 long. If we were doing a block in base 8, it'd be 8 wide, 8 long, and 8 deep. So you just have it 3 times, 3 dimensions. So you can do it with any dimension that you choose. There's nothing special about the dimension. Now, we also want to sort of remember that when we're talking about this is a power of 0. This is a power of 1. This is a power of 2. And this one is a power of 3. And what I mean by that is that if you were to write these with a base 10, this would be 10 to the 0 power. This would be 10 to the 1 power. This one's 10 squared, and this one's 10 cubed. So it's the power, the dimension that you're actually working with that you get that. But it works for any number. So let's take a look. We're going to move a little bit away from base 10, but not into the other systems that are the older systems we were working with. What we're going to do is we're going to take a look at other base systems. That is, what happens if we had, for instance, base 3, or base 7, or base 12. Now, you're going to be using some other systems in your homework, too. There's nothing special about these 3. I'm choosing one that's very, very small so you can see what happened. I'm choosing one that's still smaller than 10, but larger, okay? And then I'm choosing one that's bigger than 10 because they each have a different sort of a flair to what happens compared to what our base 10 number system does. Now, let's think about it. We talked about base 10 last time. Base 10 has 10 numerals. They start at the number 0 and they stop at the number 9. So there is no 10 in base 10. Agreed? Okay. We have something we call a 10, but it's not a single digit. Okay. Now, let's take a look at base 3. If base 10 starts at 0 and ends at 9, what do you think would happen with base 3? Still starts at 0, and it will have a 1 and a 2. So these are the 3 numerals in base 3. There is no 3 in base 3, just like there is no 10 in base 10. Okay, so think about our base system. What do we do when we run out of numerals? That is, what comes after 9? What do we have to do after we've run out of the single digits? We have to put 2 digits together, double. And the digit looks like a 1 and then a 0, right? Well, the same thing happens in base 3. After the 2, we have a 1 and then a 0. And we will read it as 1, 0. We won't read it as 10. Okay, 10 actually has connotation for us back into that base 10. So we're not going to read these as the number 10. We would read it as the number 1, 0. And what would come after 1, 0? So we have 1, 1. What would come after 1, 1?
1, 2.
And then what do you suppose would happen next?
2, 0.
2, 0. So we run out of digits just like we run out of digits in base 10. We just run out of them much sooner, right? Because I only have 3 digits to run out of. I'm going to be running out of them quite quickly. In fact, what would the largest 2-digit number be? 2, 2, right? So after I get to 2, 2, what would I get? A 3-digit number. And what would it look like? It would look like our number 100, 1, 0, 0. Okay, so all the properties, everything works the same way. And here's why this is happening. Because in our base system, we have the ones place. I'm going to do this with the number 1, 0. And then we have the tens place, correct? Well, in base 3, we don't have a tens place. We have a threes place because it's base 3. So this is the ones place, and this is the threes place. So the number 1, 0 is the number 3 because it is 1, 3. There is a 1 in the threes place. Okay, we'll do some more with that concept here in just a little bit, but that's why that's happening. How about base 7? What are my numerals in base 7? 0 up to 6. What would come after 6? 1, 0. And then 1, 1. All the way up to 1, 6. What would come after 1, 6? 2, 0. And we would keep going, right? All right, base 12 is different. Why is base 12 different than the others?
It's already a double digit.
Okay, so two things. Rachel, what did you say
It's already
first?
double digit. 12 is like
Yeah, we already say
11.
12 is a double digit. What did you say?
I said it includes the 1 0 and 1 1.
It's going to include it if we choose to write it that way, but then that's not so helpful to write it that way, right? So I need more digits than I have. Agreed? I should have how many digits? 12 digits, because I'm in base 12. Agreed? So I'm definitely going to have from 0 up to 9. But I need a digit that is a single valued something, one thing to write down that means 10. And I need one thing to write down that means 11. Agreed? I don't need a 12 because I'm in base 12, but I need two more additional digits that I don't have. So it depends on the materials you're looking at as to what you do next. The other textbook that I used to use, what it would do is it would go to the letters of the alphabet. A, and then B, C, so forth. Okay? I actually prefer that one, but we'll be consistent with what your textbook does. For 10, it uses the letter T. And for 11, it uses the letter E. And that's great as long as I don't then go to 12, and then I'm like, what am I going to use? Well, if they did need it, like if you're in a bigger base, what they would use for 12 is they'd use the letter W, just so you know. I'm not a big fan, because then what happens when I get to 13? Maybe H? I mean, I don't know. But this is what your book does. So we're going to go with T and then E. Okay, so T is the number 10 and E is the number 11. Everybody good?
Yeah.
Okay. What will come after E?
1 0.
That's when you would hit the 1 0. And then 1 1. What would come after 1 9?
T 0.
It would, not quite.
He's
What would come after 1 9? 1 T. And then 1 E.
Oh.
Right? After 1 9 would come 1 T and then 1 E. And then 2 0. Okay. These are the preceding, succeeding values, just like the other kind of questions we dealt with. This is base 5. All right? So this is the number 1 4 in base 5. We're supposed to find the preceding number, which is the easy one in this case, and then we're going to find the succeeding number, which is the harder one. So what comes before 1 4 in base 5? It would be 1 3. And we write as a subscript F-I-V-E, the word 5, written out. There it is. That tells us we're in a specific base. If you're in base 10, you don't have to write it, because that's the presumed base that we work with all the time. But if you're in any other base, you're going to write as a subscript of the base in a word form. Another thing is some books will not write it in a word form. They'll write the number 5, and it'll look like a subscript in parentheses. So I would prefer that we not, just because otherwise something is going to look like this, and all of a sudden before you know it, somebody's going to write something that looks like this, and then you're going to start multiplying something together. So this is not my favorite notation, but just to be aware of, if you see another textbook using it or something, that's what they're doing. They wouldn't write the 13 at the end with the times 5. But. All right, so what's going to come after 1 4 base 5? 2 0, because I'm out of digits, right? I can't take 4 and turn it into a 5 because there is no 5 in base 5. So I've run out of digits in the 1's place, which means my 10's place, which is really my 5's place here, but the second digit over has to increase to the number 2. My 4 will become a number 0. So this is 2 0 base 5. We're going to do the next number in reverse order. That is, we're going to do the succeeding term first because it's the easier one. This is base 12, and I have T 0 0. What would come after T 0 0 in base 12? T 0 1. So that was pretty simple. You guys got that no problem. 1 comes after 0. Preceding is harder, though. You see, because I've got a 0 on the end. So what in the world am I going to do when I've got a 0 on the end and I want to go before that, that is the number before 0? We're going to do, in essence, subtracting, right? I mean, really what we want is we want T 0 0 minus 1. I mean, that's the number before. Well, how do we do that? Borrowing. Yeah, and I'm actually going to write it down like that, too, to give you sort of a reference to think about. we're going to do a borrowing feature. So I need this 0 to become what it is in this base system. So what is the biggest value in base 12?
E.
It's actually E. Or if you want to, for the moment, you can remember, that this is the number 12 that you're borrowing. And when you take your 12 and you borrow 12 from the column before and subtract your 1, you're getting 11 down here. I'm putting it in parentheses just to remind you that that's not really what we're going to write down. But I've got 11 of them. I'll show you another way to think about this in a minute. This 0 right here would have been a 12 as well. But then I borrowed from it in order to get it over to the 11, or to the 12s. I borrowed from it in order to get the 0 next to it to become a 12.
Wait, why are the zeros changing to 12s and not 11?
Because I'm not going with the number before. I'm borrowing from the column over.
Well,
I'll show you why in our number system. You're going to be like, oh, yeah, that's exactly what I do. So hold tight for me for just a second. What will the t become? A 9. All right, so this is going to be 11 down here as well, and this is going to be a 9. So this actually becomes 9EE. Base 12. Okay, so let me do the exact same thing, but in our base 10, and you can agree that this is what we do. Let's say that the number, instead of being T00, were the number 800. Okay, and we're subtracting 1. What do you do when you subtract the 1? Well, you can't take the 1 away from 0, so what does the 0 become? Does it? It becomes 10. Because then when you subtract, you're going to get the 9.
But usually, if you're subtracting like that, you would start at the 8.
Okay, that's fine. So start at your 8. Your 8 becomes a 7. Your 10 here, your 0 becomes 10. And then you make that a 9. Exactly.
Can you work that way on those?
Mm-hmm. Sure. Sure.
I think I was confused.
And I'm going to show you one other way to think about it too. I suspect if you wanted to find the number before 800, you wouldn't really subtract, right? No, what you would actually do is you'd say, okay, well, the number before is going to have 1 less right here, and these two numbers are going to be the largest number that there is in that base system, which is a 9. So they're 9 and 9. You do the same thing over here. You find the number before the t, that's a 9, because t is 10, so that's number 9. And then you change these zeros to become the biggest number that there is in base 11, or base 12, which is an 11. So they're E and E. So you don't have to actually do a subtraction feature if you're thinking about just the number before. You just want these numbers to be as big as possible at the end, just like we do with 9s. The number that comes right before the 0, 0 is the largest number possible in the 1's place and the 10's place. They're 9s. So that's why these are E's. And then the t, 1 before t is an e, or 1 before the t is the 9. So you have 9EE, base 12. All right, let's do something more fun. What we're going to do next is we're going to actually take whatever base that we're in, and we're going to turn it into base 10. Okay? So I want you to write down, or circle, actually, since it's already written here for you, I want you to circle the word multiply. The key thing that we're going to be doing when we turn any other base, so base whatever, into a base 10, is we're going to be multiplying. Okay? So here we're going from base 2 into base 10, which means we're going to multiply. That's the key thing we're going to be doing. Now I'm going to expand what I'm actually writing out a little bit so that we can see where the multiplication is coming from, because it's a little bit small. This is the same number I already had, 1, 0, 1, 1. It's in base 2. So the fact that it's in base 2 means that each of these placeholders is a power of 2, right? Just like in base 10, each of our place values is a power of 10. So the first one is the 1's place, or 2 to the 0. The second one would be our 10's place, so it's the 2's place, or 2 to the 1. The next one would be the 2 squared's place, right? 10 squared is what we would have, which is 100. And the last one, or the first one listed, if you will, is the 2 cubes place, which would be our number 1,000, because it would be 10 cubed. So these are powers of 2 because I'm in base 2. They're really good so far? All right. What we're going to do is we're going to take each of these values times its placeholder. That is, I want 1 times the number 2 cubed. Plus, and I'll write it out even though I know it says 0, but 0 times the number 2 squared, 1 times the number 2 to the 1, and 1 times the number 1. So I'm taking the value in that placeholder times the placeholder's value. It's the same thing that you think when you see the number 623. You don't think 6. You think 600, right? It's the same thing. It's just a familiar base, whereas this base 2 is not so familiar to you. All right, so let's actually change this into that value. So I have 1 times, what's 2 cubed?
8.
Good. Plus, this is a big old fat 0. I've got 1 times 2 here, which is 2. And 1 times 1, which is 1. So and then 8 times 1 here is 8, of course. So I have 8 plus 0 plus 2 plus 1, which is 11. And if it helps you to write the TEN down beside it, like this, you can. You certainly don't have to. But this is in base 10. This is equivalent to the number 11 in base 10. Does anybody know where base 2 is used? It's actually practically used. Yeah, it's used for binary for computers, computer programming. So base 2 is a computer programming tool because it means the switch can be turned on or off. There's only 2 positions for a switch inside of a computer. So base 2 is actually used. It's not just I made it up for it to be fun. Okay, it's really a useful number system. There's another base that's used in computers. Does anybody know what it is? Do you know, Carrie-Ann? Hexadecimal. Hexadecimal is base 16. Hex, 6, and then decimal, 10. It's base 16 is another system that's used for computers. Okay. All right, let's do base 12, and then we'll talk a little bit about some other number systems that are used. I'm out of space, so I'm going to actually delete all my red pieces. Does everybody have everything written down that they need? Okay. All right, so this number is T00 base 12. So I've got 3 placeholders. I'm also still going from base 12 into base, in fact, I'm going to write this down here, the answer from above, because we're going to compare something in a minute. This is 11 base 10. Okay, 12 into 10. And anytime I turn something into base 10, I multiply, right? So I'm going to be multiplying. I have a T and then a 0 and a 0, but I really don't want to write T. I'd like to write what T's value is. What is the value that T represents to us?
10.
It's 10. So I have a 10 in this placeholder. Because eventually here I'm going to be multiplying in my number system, so I'd like to write it as a number that I think about. Does that make sense? Okay, this is base 12, so this is the ones place. You're always going to start with the ones place on the right. What's the next place value going to be? 12, because I'm working with base 12. So this is 12 or 12 to the 1. What's it going to be when I come over here to the third place to the left? 12 squared. Now, fortunate for us, we've got some zeros in here, so I'm not going to have to do as much multiplication. But I really have 10 times 12 squared plus 0 times 12 plus 0 times 1. So you might be asking yourself, how much do I actually have to show with what I'm working on? This step you have to show. The step that shows the pieces that are going to be multiplied. Before that is your choice, and after that is your choice. But that step you have to show me, because that's the step that actually shows what each value is being multiplied by in terms of its place value system, okay, in the place value system. All right, so just for our benefit, we're going to write down, what is 12 squared? 144. Do you remember exponents come before multiplication, so don't you go multiplying 10 and 12 and then squaring them. You have to square first. Okay, and then of course 0 times 12 is 0 and 0 times 1 is 0. So I really just have 10 times 144 or 144, which gives me what? 1,440, and this is base 10. Again, you don't have to write the 10. I'm just going to do it right now to remind us that that's what we're doing. I want to show you something that's a good question to ask yourself. We talked about problem solving in chapter 1, right? And one of the things that we talked about when we were doing problem solving is looking at an answer at the end and deciding, is it a reasonable answer? Is there some sort of sense it makes? Okay. There is a way to think about this when you're working with these, and we'll do the division, and it'll have the same feature in just a minute here, doing them in the other direction. If I start with a bigger base, and I'm going into a smaller base, which is exactly what happened on this last one. I had base 12, which is a bigger base, into base 10, which is a smaller base. The number actually looks like it got larger. Do you see that? I started with a 3-digit number, now I've got a 4-digit number. And if I start with a smaller base, that is base 2, and I turn it into base 10, the base was smaller to start with. It was base 2. The base is bigger to end with its base 10, and the number looks like it got smaller. It started out with 4 digits, and now it has 2 digits at the end. Now, it won't always have fewer digits, although often it will, but even if it doesn't, when you compare the numbers, it will look like a smaller number than it was before. Okay? So when we're working, anytime we're working and we're comparing the different values within the different bases, smaller base, bigger value, bigger base, smaller value. All right, we're going to go the other direction now. All right, this is converting anything in base 10 to anything in some other base. So from base 10 into something else. And I absolutely love the way that your textbook shows how to do this because it does a nice, they call it, I don't know if they call it that or if I call it that, but it's a division scaffold. That's what it really is. It gives me a set way to do it so that I don't have to remember all the pieces. And this is the first textbook that I've seen that's done that I've used with this content. Okay? So the first thing to recognize, just like we did on the previous slide, is that this is going to use division. So if you're starting in base 10 and you're turning it into some other base, division is what you're using. Okay? So notice I'm starting in base 10, 11028, right, 11,028, and I'm turning it into base 4. I'm going to divide because I'm changing from base 10 into something else. So here's the way that this works. The first thing we have to do is we need to write out some powers of 4. Because if I'm turning it into something that's in base 4, I need to know what the powers of 4 are. And we're going to write out all the powers of 4 until it's very clear to us that we've got enough of them. And I'll explain when we get there. So the first power of 4 is 1. It always starts with 1. And the second one is 4 because we're working in base 4. The next one should be 4 squared. But what is 4 squared? 16. And then I've got 4 cubed. What's 4 cubed? Good. I've got 4 to the 4th. What's 4 to the 4th? I think it's 256. Somebody check for me. Is it 256? I could look on here, I guess. 256. All right, you're definitely going to need a calculator after this. How about 4 to the 5th? 1024. How about 4 to the 6th? 4096. How about 4 to the 7th?
16,384.
And that's too big. Not, that is that your answer's wrong. But that number, once we got there, tells me that I've gotten a number that's too big. Why?
It's the same amount of digits.
Well, yes, but it's
Bigger.
bigger.
You're missing a 6.
Oh, did I miss something?
It's 4096.
Oh, I'm sorry. I see what you're saying. Right there?
Yeah.
Okay. Sorry about that. Yeah. This number at the end, 16,384, is bigger than the number I'm dividing. That's how I know I'm done. I'm looking for all the powers of 4 that are smaller than the number that I'm dividing. Is everybody with me? So this number I do not need. And I don't really want to think about these numbers right here, but these are the powers. But these right here are the numbers that I'm going to be working with. Okay, these are the expanded form of the powers that I need. Okay. So what we're going to do is we're going to divide the number we're given, which is 11,028, by the biggest power of 4 that goes into it. And that biggest power of 4 in our problem is 4096. So we're going to write it like this. 4096 on the outside. Hang on. Yeah. It's a little bit too long just for purposes of writing. 11,028. So this looks like division until I did this weird little step on the other side. And then the step on the other side is going to help me out in order to find all my answers. Okay. We're going to divide, and you're going to use your calculator, which is just great. So take your calculator. What I want to know is how many whole number times will 4096 go into 11,028? What's the whole number you get when you do the division? 2. All right, so you did 2. And then you need to kick your calculator or do it in your head or on paper or whatever, and you need to multiply 2 times 4096. What do you get? 8,192. And you're going to subtract to get what would have been a remainder if you were working with a traditional division problem. So what do you get when you take 11,028 minus 8192? 2836? Excellent. And so we're going to tick off going down this list one at a time. I've divided by 4096. The next thing I'm going to divide by is 1024, excuse me. Even if it didn't go in, I would use it. So we're going to have that happen here in a minute, but I just want you to recognize we're going to use every single power that we wrote down. So how many times will 1024 go into 2836? 2 times. What is 2 times 1024? 20 what? 48. Perfect. And we will subtract. So what is 2836 divided, I'm sorry, subtracting 2048? 788. We're going to use our next power of 4, which is 256. How many times will 256 go into 788? 3. What is 3 times 256? 768. Which I subtract, I get 20. All right, I need some more space, so I'm going to move a little bit of this up a little bit. That wasn't quite what I wanted. Let's try that again. All right, I think that'll work. All right, so we had 20. What is the next power of 4? It is 64, and I fully recognize, just like you do, that 64 does not go into 20. But I promise you want to include it right now, and I'll show you why in a minute. So 64 doesn't go into 20, which means it goes in 0 times, and 0 times 64 is 0, and 20 minus 0 is 20, and I know it feels like we didn't do anything, but I promise you want it there. Okay, just bear with me, and I'll show you in a minute. What's next after 64? 16. Does 16 go into 20? Yes, it does. How many times? What's 1 times 16? What's 20 minus 16? 4. What's next? Next power of 4 is actually 4. How many times does 4 go into 4? What's 1 times 4? Good. And 4 minus 4? 0. We will not end this process until we divide by the number 1. I recognize we don't have anything to divide, which means that the number of times it's going to go in is 0. Here's why we did all this in this way and we're so meticulous. Do you see all that I just highlighted in blue? That's your answer. And if you skip any of those powers, you're going to skip one of the zeros. All right? So 2, 2, 3, 0, 1, 1, 0 with a subscript 4 because it is base 4. That's your answer. Base 10. The number was 11,028. Had 5 digits, was base 10. In base 4, the number looks bigger, and the base is smaller. Are you with me? Okay, we're going to try another one. One more, I think, is exactly what we have left, right? All right, this is a wonderful number. It's 99,999. We're going to put it into base 9, and base 9 has no 9s. Okay? All right, so we need to know the powers of 9. So grab your calculator, help me out. We've got the number 1 and then the number 9. Then I've got 9 squared, which is 81. So what comes after 81 in your powers of 9? 7 what? 29. What's after 729?
6,560.
Perfect. And what's after that?
59,049.
Okay. And I contend that that's got to be big enough because our number is only 99,000 and that's already 59,000. If you wanted to confirm that, multiply by 9 and it's going to be way too big, right? So these are the powers that I need. So I will start with that largest number, 59,049. I will use that as my divisor to the number 99,999, and it will go in exactly how many times? Once is the right answer, yeah. What's 1 times 59,049? 59,049, you betcha. And then we're going to subtract. All right, so what do we get when we subtract? Perfect. And then we will divide by the next largest power of 9, which is 6561. So how many times will 6561 go into 40,950? 6 is correct. What is 6 times 6561?
39,360.
Excellent. Which we're going to subtract. So what is 40,950 minus 39,366? What is it? 1584. Great. Next power is 729. How many times will 729 go into 1584? 2. What is 2 times 729?
1,458.
Perfect. And if we subtract, what do we get? 126 is correct. Good. My next power is 81. How many times will 81 go into 126? Once. So if I multiply, I get 81. 126 minus 81 is 45. My next power is 9. How many times will 9 go into 45? 5. 5 times 9 is 45. And while I do recognize that I'm at 0 as my sort of remainder, I'm not done until I divide by 1. Sorry, I ran out of space. How many times does 0 go into 1? 1 go into 0, I said it the wrong way. How many times does 1 go into 0? 0. Okay. All right, so my answer is here on the end. 162,150. Base 9. Okay, so compare. In base 10, the number was 99,999. In base 9, the number is 162,150. It looks bigger, right? And I only went down one base this time, and I still got a number that looked bigger than it did before. Okay, everybody kind of okay? I mean, you're going to have to practice, and I get that, but are you okay right now? Okay.